Hello, can you hear me? You can hear me, right? Okay. So last week we discussed about generative models, right? Like GANs and VAEs. This week's content covers diffusion models. So yeah, it kind of builds over VAEs. So let's just review what happens in VAE. So in VAE we have it's an auto encoder, right? So we have an encoder and decoder where we while training we give the input images, encode it into a latent variable z, and pass it through a decoder to decode the image, and then we have a and then we'll have like a mean squared error loss between the input and the generated image, so that yeah, you train the encoder and decoder so that the latents learn to represent the real images. And so the objective with which it was trained was this elbow objective, where this is the likelihood, data likelihood, where it is a measure of how good your decoder is, like how well can the generated image represent the real images, right? So this is what the this likelihood part measures how good the decoder is. And then the other is, this is the prior matching term, which measures how good the encoder is. That is, we approximate like z to be a uh, standard Gaussian, right? So this is a standard Gaussian, and how well is this encoded q, like which I get the latent, approximate the Gaussian distribution. So this is the prior matching term. So by optimizing the whole network in an end-to-end manner with this objective, we learn the encoder and decoder, and then we have a trained VAE, right? On a data, on a real data set we would learn. Yeah. So yeah, while training we have a input image, we encode it through the encoder, which gives the mean and variance, right, of the latents. From this we sample the latent Z, pass it through the decoder, and we get the image. And then this is the objective, the reconstruction objective. So this is the reconstruction objective here. This is the reconstruction, and then this is prior matching term. This learns the encoder and this learns the decoder, and you train the VAE. After that, so once you train the VAE, you can get rid of the encoder, right? Like this whole part is not required anymore. So you sample Z from standard Gaussian, pass it through a decoder, and you get the image. So that is how you use VAE in inference. So this DDPM, denoising diffusion probabilistic models, are commonly known as diffusion models. So it can be thought of as a hierarchical VAE. So what we are doing in VAE is that we start from the input image space, and through the encoder we project it to a standard Gaussian space, right, like to the noise space, and from noise we are directly decoding to the image. So in DDPM that is done in steps, like I start from an original image and I keep adding noise in stages, and eventually with time so this would be standard Gaussian. So you can think of it like the rather than going from image to noise, it's like encoder adds slight amount of noise, and then decoder learns to denoise it in a stepwise manner. So you pass the image to the encoder, you keep getting intermediate latents, you keep passing them to the same encoder until at some time step you encode the image such that it matches standard Gaussian, and later to generate images you start from standard Gaussian and you just do this denoising process, passing through the decoder to get in order to generate images. So this is how DDPM structure would look like. And here all the encoders are the same, like weights are the same, it's the same encoder, but you are repeatedly encoding the image. Even here same weights across time. So it's like, so from 0 to t, so some capital T number of steps. So T is usually set something like 1000 time steps. So you start from a real image and you go to the noise space in 1000 small steps, and then you do denoising starting from a noise, sample noise, then you do denoising to generate like fake images. So this is how the overall structure of a DDPM or diffusion model is. Any doubts on this? So these are all like these intermediate terms, these are intermediate latents, unlike just Z. So this here this last latent, so xt becomes equal to the Z in VAE. This is a hierarchical VAE at tth step, which is at 1000 step. So these are all intermediate states or intermediate latents. Is this clear? Any questions or doubts on the overall structure, architecture of a DDPM? So all the recent generative models which you would have all used, like stable diffusion, flux models, or anything in even all these in Gemini and all what you use the generative, the fundament, it's all the underlying model in all of them is actually diffusion models. There are improvements over the architecture and all that now, like they don't take these many time steps to generate an image, make it faster, not doing in image space but they do it in latent space. All such things are there, but still the fundamental idea is still the same. So yeah, the three states and three building blocks of DDPMs are this. So there are three different states. One is X naught. That is the original image, like this one. Original image where I am starting from. So that's the original image. So this is same as what we saw in the VAE, like it is equivalent to X. And then all these x1 to xt are intermediate states, as I said, and the last one xt is the final latent variable. So this is equivalent to the z in VAE, and all these variables x1 to xt all are modeled as Gaussian random variables. I mean, in fact, so x naught is real, x1 to xt are all modeled as Gaussian random variables. And how the extent, how much noise is added at each time step. So this whole schedule is curated such that when it goes to time step capital T, it becomes standard Gaussian. So that is how these are modeled. And yeah, there are three blocks in this network. That is the initial block, transition block, these intermediate steps, and the final block. Three blocks in the sense it's in terms of the architecture. So this is the first block where it goes in the connects to the next state in the towards its right, like this is the first block. And then here this is the intermediate block, the green one what you see. So that state connects to the previous state and the next state in this fashion. In the forward process it connects to the next state, in the reverse process it connects to the previous state. So it communicates in this way, and this is the last block. So there are three fundamental building blocks in this and three kinds of states in a DDPM. Is this clear? Any doubts on this? Yeah, so this is how the building blocks are, right? So the first block is the first step of adding noise, like noising the input image, right? You go from x0 to x1. So there is no forward step here that connects the state 0. So so this is the last reconstruction step. So you are going from, so here only the decoder is involved because we start from um, x1 and we want to generate x0. So this is what we are trying to learn, and it is approximated in this form. So p of x0 given x1 is what we want, and it is parameterized through a Gaussian in this form, pt of x0 given x1. So this is the same as like it is similar to p of x given z, which was approximated as that q phi of x given z in VIE. Is that here it was the latent, the noise, here it is the first latent. So like x1 here becomes equivalent to z in VIE. And then this is the transition block. So here there are three states involved: the previous state, current state, and the next state. Um, so in the forward noising process, forward sampling process, we're going from xt minus 1 to xt. So this involves the encoder. Through the encoder we do this, and then this involves the decoder during the denoising process. So here we are trying to model the encoder, that is p of xt given the previous state xt minus 1. So which is also approximated by a Gaussian, which is q phi of xt given xt minus 1. And in the denoising process we are trying to learn or model p of xt given xt plus 1. So we don't know what exactly this is, and this is modeled in the form of a Gaussian given by like pt of xt given xt plus 1. And this is the final block. So this is like the decoder part, right, in VIE. So yeah, from the previous time step xt minus 1 we are trying to model xt, and that is also approximated by standard Gaussian, by a Gaussian. So all random variables are modeled by random variables, their conditional distributions, everything is modeled by Gaussians. So this function q of xt given xt minus 1, right, here this is modeled as we have written here, it is modeled as Gaussian, and the variable it depends on is xt minus 1, right? So q of xt given xt minus 1 is given by what, yeah, so xt, and it's with its mean as root alpha t xt minus 1 and 1 minus alpha t into I. So this is the mean and this is the variance, right? So xt would be of what form? It be like root of alpha t xt minus. So if this is the distribution and this is how the sampling would be, right? This is mean plus square root of 1 minus alpha t into I, this is the variance into epsilon. So epsilon will be sampled from standard Gaussian. So this is how the latent variables are related. I'm right, no? Anyway. So this is how the all the latent. So starting from x0, this is how you can compute all the intermediate latents. But you need these terms. So what are all these? There is alpha t, right? Alpha t, yeah. So alpha t um, is a parameter, right? It's a parameter. And so how do we choose alpha t? What is a constraint we have on how these alpha t should be? So what am I trying to model? So this is a transition distribution. So from x naught I go through all these intermediate latents, so xt blah blah blah, and finally I get to xt, and this I only know xt, which is supposed to be this, and I don't know what. I know these are Gaussians, so I'm modeling them as Gaussians in this form, but the parameters of that Gaussian variable, I mean Gaussian distribution, is alpha t, right? So how should alpha t be chosen? Like if I know only this and I want x t, capital T, to be this, so what? How should we choose alpha t? Like depending on what? What is a constraint we should impose while choosing these intermediate alpha t's? At last time step, alpha t should be alpha should be 0 to xt as pure Gaussian, not alpha t. Alpha t should end up, yeah, right, yeah. So yeah, you should choose alpha t such that at the end your capital xt will become this, right? Correct. So yeah, that's what. How do you choose this alpha t? Why is it chosen in this form? Is because I mean the form of this function is chosen in this way in order to make that. I mean, if you choose it in this way, then xt will become standard Gaussian when t is large enough. That is why they chose uh, these parameters. Yeah, I think there's a whole derivation of how they get that, but I think it's not important. So this is transition distribution. That is, how do we relate two consecutive latents, right? And anyway, at the end we are starting. Okay, yeah. Where did I put the? Shit, forgot. Okay, actually, all this whole process is modeled as a Markov process. The intermediate, all the latent variables, right, follow the Markov property. That is, uh, like every next state depends only on the current state. Like I know that x t will depends only on x t minus 1, and it doesn't depend on any of the earlier states. Once we know what xt minus 1 is, then I can say what xt is. So that's how that function is, right? So xt depends on what it is, some root alpha t xt minus 1 plus 1 minus alpha t into epsilon. So I have only this one random variable involved. So given this, I can say what, I mean, I can compute what xt is, but I don't need all the previous random variables. So that is the defining property of a Markov chain. So the probability of going from one state to another in a Markov chain is usually written as a transition matrix P, where, so if there are n states, and this is how the states are related. So here Pij represents the probability of going from state I to state j. That is probability of going from state I to state j. So can you say something about like a characteristic of this matrix? So starting from state 1 in this image, where can it go? From 1 we can go to 2, we can go to 1. That's all, right? Oh yeah, n. 1 we can go to 2 and n. So can you relate these numbers in any form? P11, P12 plus P1n. What should this be? From 1 I can go to 3 different states and all 3 are probabilities. So how would they be related? Sum should be 1. Yes. Yeah, so this should sum to 1. So every row here represents the probability of going from the current state, whatever that row is I, to every other state possible. So some of these can be zeros also, right? Like here, when I'm saying this is equal to 1, I'm also saying that P13, P14, P1n minus 1 are all zeros because they are not connected, right? State 1 you can't go to any of them. So what this says is all of this sum to 1. So row sum of a transition matrix is 1 for all I. So this is a property of a transition matrix of a Markov chain. So this is conditional distribution, that is q phi of going from x, from the starting state to time step t. So this is basically a composition of all of this, right? How you go from x0 to x1, x1 to x2, blah blah blah, and eventually you get to some intermediate state xt. So how are these alphas? So now we know this, right? This is what. So we know this, and from this can we compute what q phi of xt given x0 is. So it turns out to be this, square root of alpha t bar x0 and with variance 1 minus alpha t bar into high identity matrix, where alpha t is the intermediate schedules which I have, right? The alpha 1, alpha 2, whatever until time step t. It's a product of all of them. So they look very similar, but they're not exactly the same. Using grid q phi of xt given xt minus 1 given square root of alpha t, this is xt minus 1 comma 1 minus alpha t into I. This is alpha t bar and this is alpha t, and here the mean depends on x0, that is the original image. Here it depends on the previous latent. So if you look at how this um, this intermediate transition, that is q of xt given xt minus 1, right, how these would be, eventually it looks something like this. So initially say the Gaussian was like this with a peak here, with a peak at this place and this place, something like this, no, what you're seeing here, this, if you see it in 1D it will be something like this. And eventually what do I have a peak at 0. So this is 0 comma I, this is p of xt. So you are choosing, by choosing alpha t carefully, where irrespective of where you start, you're eventually converging towards a Gaussian for large time steps. This is basically as t tends to infinity, it has t tends to infinity, we are saying that xt converges to, so like, yeah, this is a 200 time step, a good number of steps, and it converges to standard Gaussian. So this I mean these lines here which you see, right, that is if a sample is at this point originally, uh, when you sample, like if x naught is at -2, suppose, when you sample x naught, I mean your real sample, right, real sample is here, then by following this Gaussian, I mean this Markov process, it will take this trajectory, like at x1 it would be this value, blah, so at x20 it is here, at x40 it is here, blah blah blah, such that eventually this is the value at x200 for this sample where it started from -2. So irrespective of where you are starting from, eventually it converges near the such that like xt looks like a Gaussian. So that is what this trajectory shows. Is this clear? Any questions?
Yeah, so I have hello, I'm
Yeah,
audible?
yeah. Tell me.
Yeah, so probability distribution to normal 0 1. So till the time the distribution becomes normal,
Mm-hmm.
the trajectory will change, is it? Like while moving from state 1 to state 2, is it? Because I heard that there is some differential equation, means whenever there is state transition, then we take the derivative of previous state. So I just want to understand in terms of a derivative, like when we take the gradient of, I think, yeah, that's what the case is here.
Yeah, you are defining the how you are defining these latent variables, right? um, how they're related, they're related such that if whatever where you start from, you will eventually end up like this, just by using the form here, like this has nothing to do with gradients or derivatives in this. It is just following that process, no, like xt is equal to square root of alpha t xt minus 1 plus 1 minus alpha t into epsilon, this one, this term. So but you obviously you're choosing alpha t in a careful manner such that you end up becoming end up converging near this.
Okay, so means for reaching one state to another state, we are using this equation, right?
Yes,
There is no
yes.
derivative concept. Okay,
No, no.
thanks.
This trajectory is obtained on changing beta schedules. Not necessarily, this is not really that, this is just different samples at so at x naught it is real data, right? Real samples which I have. So if x naught is equal to -2, this is how the trajectory would be. So if you take this point here, here x naught is probably some 2.5 or something. Here it is something very close to like 1 or something. So it's like for different x naught, what will your xt be? So different x naught. How does the trajectory change with t? And eventually converge to for large t. So how is DDPM trained? It is again very similar to the VIE thing, because it is essentially hierarchical VIE, right? Like the first block and the last block become sort of equivalent to how you train the VIE. And but there we have also have these extra transition blocks in between, right? So you have to account for that. So the objective to train this DDPM has three terms. The first term is the same. This is the data likelihood term. So which kind of measures how good the initial block is. That is your last decoding step, right? Like coming from an intermediate latent to the image. So how good the initial block is. So this is the first. This is also there in VIE. Also there in VIE, but it's not x1. X1 is equivalent to z in VIE. And this term is the prior matching term. So this is my last prior, right? Like at half, when I go from the previous latent xt minus 1 to xt. So this, how good the initial block is. This is also about the decoder, right? This is the decoder loss type. Theta is the decoder. Phi is the encoder. So this is the prior which I am modeling through a parameter. Parameterized by phi. This is the real prior, right? This is standard Gaussian. So this is the prior matching loss. I want this to become equal to this. So this is also there in VIE, but in VIE it was like q phi of z given x, KL divergence of this with p of z. So it's equivalent to what is there in VIE, but with different latents. Here it's the previous latent, here it's the first latent. And then we have this transition blocks, right, in between one. So in between, why do we have this term is because, so we have two things, right? One is the forward process and then it's in the reverse process. So from xt minus 1, I go to xt. From xt, I go to xt plus 1 in the forward process. In the reverse process, I come from xt plus 1 to xt and then to xt minus 1. But what am I trying to learn? Whatever I am encoding in the forward process, I want to do the opposite and undo that in the denoising process, right? So this encoder and decoder should learn the exact opposite thing. If the encoder takes my latent from xt minus 1 to xt, decoder should bring the exact latent from this. So in the encoder, I'm going this direction. I mean, to get xt, I need xt minus 1. But in the decoding process, I come to xt from the next step, right? So q phi of xt given xt minus 1 is the forward process. So whatever xt I get from this should also be the same xt which I get in the reverse process. In the reverse process, what do I do? Decoding one, so that is p theta. I am starting from the next latent, right, the noisy one, which is xt plus 1. From there I come to xt. This is noisier than this. This is because I am decoding it. So this is the reverse process. So both of these, this xt and this xt should be the same, right? If I'm taking the same real image this way and this way, both of them should be the same. So that is why there is this scale divergence term that models xt. This is in the uh, yeah, encoding part, forward process or forward process, and this is the decoding or reverse process. Both xt should be the same even I arrive in different directions. So that is why they extract KL divergence term to match the priors, both these priors. So these are the three elements in uh, training the DDPM. Is the idea clear? Obviously it's way more involved, but at the high level
Yeah, so I just want to know, like how this algorithm will know that till the time the distribution is the normal distribution, it will keep changing the states.
the algorithm will not know you are. So this alpha t is no, which we discussed, is chosen manually.
Okay,
So this is already fixed. So because you are fixing this alpha t, the schedule is fixed. This is what we call a schedule, the denoising schedule. So this schedule is fixed. So it will go to it is chosen such that at certain step it will reach. It will be almost normal. I mean, obviously, you'll assume some big number t and assume that is like infinite, like here t is equal to 1000. You just assume t is equal to, I mean, sort of approximating infinity to 1000. So, like in 1000 step, it will sort of become Gaussian, is your assumption, and alpha t is chosen like that. So,
so is there any heuristic to select that parameter, or
which one?
this t parameter, so that you are saying that eventually it's going to be the normal distribution in the end, right?
So, if you choose this formula, right, which we have chosen here, uh,
Okay. Hello.
yeah, so alpha t is a number between 0 and 1, obviously. So once you choose this, I'm not very sure about this, but as long as this alpha t is lying between 0 to 1 and you choose sufficiently big enough capital T, um, it
Okay.
should converge to 0 to 1. Like for all
Maybe there is some while condition, like if it is going beyond 0 and 1 condition, then probably it's not the normal distribution. So is there any while loop in the algorithm that it will auto exit it? So it will say that now your distribution is normal distribution, and
you
now
can never say that, right? How can you say these are all samples? You can never say that what do you call as normal distribution? So
So there must be some definition. That's how there must be some exit criteria where still when the forward process will go on.
So that you're fixing, no, this T is fixed, capital T. So I say 1000 steps, 1000 I'll
Okay.
do, that's all.
Like epochs, you are fixing it.
T, this
It
this
may
number
reach
of,
it may reach a normal distribution during that t equal to 1000, or it may not reach.
so that's what it's sufficient. If you take it sufficiently big enough, then it will reach. That's how it is.
Okay. I
You
think yeah,
can't
it's
really say, see, here it is, they're showing time step 200, right? But here itself, it almost looks like normal.
okay.
So so if you added, so this is how this noise, you start from image, you keep adding this, right, noise in this way by choosing this alphas, so alpha t between 0 and 1, and you do this. So after some point it will look like look like it's sampled from Gaussian noise. You can't really say it's a real image, right? It look like Gaussian.
Okay.
So yeah, the thing is t should be big, sufficiently big.
So yeah, so it will keep on running forward process till t equal to some
Yeah,
1000 or
you
whatever initial it was.
theoretically t is infinity, but you don't do that, right? Practically we
Okay.
choose a big number and say at that number, like, it has become noise. You can keep adding more and more. It will still become, for practically it look like Gaussian, but I mean, when are you theoretical proof is that with infinity only it will become Gaussian, right? You can continuous random variables, but
Okay.
you
So
choose
that's why some big number we have
you
to
choose
take.
big T. Usually it's like 1000 steps. It is.
Okay. Got it.
Like in this term we saw, yeah, this conditional distribution, right? So at cap for capital xt, if I have to write this q phi of the last latent which I'm choosing, xt given x naught, what is the mean of that? Square root of alpha bar x naught, right? And the variance is 1 minus alpha t bar I. And here what is alpha t? So I have written alpha t is this, right? So I want this to become 0 because I want this to match 0 and 1, 0 and I. When will that happen? It will happen, it will exactly become alpha t when this whole product becomes 0. And this, yeah, if this whole product becomes 0, and then the variance becomes identity, I mean identity matrix, right? So but when you choose all alphas less than 1, for large t this converges to 0, right? For t tending to infinity it will converge to 0, but you can't do that, so you choose a big number where you it's practically converged type.
But only the thing is, it will require more compute. If, for example, at 500 step only, it is attaining that normal distribution,
Hmm.
then 500 step will not be required, right? But we
500
don't
also
have
might be
anything
sufficient.
normal, so
If you take more, you will get, I mean, you're modeling it better. Mm.
modeling better, but compute
Compute, yes,
scales.
compute definitely scales with time. Yeah. So most, when this came, they were doing 1000 steps, but recently the number of steps to denoise have reduced. They just do it in even like 3-4 steps. There's also like one shot, I mean, single step denoising also. There are, I don't know exactly, but I know that this number of denoising steps, even just countable number of steps, they're able to do just by changing how this, the process at the end, the process is still the same, like you're going in intermediate stages from 0 to, I mean, real to noisy and denoising. But instead of denoising at 1000 steps, it's like if I have to generate an image in this fashion, I have to go from what, start from 1000th step like noise, go to 999, like start from x thousand, then I do this to get the one small denoised version, then x998 and so on till x naught, right? I'll have to take 1000 steps. But like there are some shortcut models where they do, instead of doing 1000 steps, they do in like 4 or 5 steps. But when I say 4 steps, it's not going from here to here. That's like going from, you're bypassing this, you're coming to like 750, how the denoised image would be, then to 500, then to 250, and then x naught. So in 4 steps they do the whole denoising instead of 1000 steps. But the assumption theoretically is still the same, that you do 1000 step noising and adding noise, and in 1000 steps you denoising for faster efficiency. These hacks, this how they schedule the equations will change to do all these things, to denoise, but the process still remains the same. Does that make
Okay.
sense?
Yeah.
So even in this, we have these terms, right? Yeah, now we have to model these different terms which are there. We have, one is this term. Okay, that's very confused. Yeah, basically so this is the decoder block, right? Like whichever you have, p theta will be decoder, and the other one will be encoder. And by that, what are we trying to model? We are modeling this function, right? This equation. So how do you do this? We want to go from this to this, and model that using a neural network. That will take you from xt to xt plus 1 or xt plus 1 to xt in the forward way process or reverse process. Okay, this and all, I'm not going to go in detail. So this is how the forward sampling process would look like. From x naught, I, oh, oh yeah, so instead of using that formula of xt is equal xt depending on x1, the same thing you can rewrite in the it depending on the original one and noise. But here it has this alpha bar, right? Instead of, so both are equivalent actually mathematically. So once you choose the time step, you using this formula you can get xt, the noise. So from this step I can directly get what xt means by this formula. So yeah, but both are equivalent, there's nothing different in both. So from here it's like I'm adding noise till some big T, capital T, and so this is the joint distribution of random variables. These are all the latents, right? Latent. And this is in this form because of the Markov property. Because xt, my current step only depends on the previous time step and not anything before. So this comes because of the Markov property. So this is what equivalent to saying q of x1 given x naught, q of x2 given x1, so on to q of xt given xt minus 1. And what is this q? Is this an encoder or decoder? I mean, q is modeled as encoder or decoder? In which direction are we going? Encoder, right? Because from current step to next step I'm going, so it is modeling the encoder. Yeah, so this q is basically modeled as an encoder parameterized by phi, a neural network. Yeah, so this is how we are modeling the encoder, right? So if this is how the data is initially, the trajectory which I saw earlier, right? This is the same, just like 1D cross sections of them. If you see, this is how it would be. So this is how xt is transitioning with time. Xt would go in this way, this way, this way, and eventually at some time step it becomes like this. So how do we train this DDPM? So obviously you need a training data set. At the end it's learning reconstruction, right? Like encoding and decoding. Um, so what we do is we pick a random timestamp t between, so this capital T is fixed, right? You fix t, pick some random time step, say t is equal to 50 at some instant. So keep iterating. At every step you pick some random t and then sample xt following this distribution, right? This is what we defined earlier. Following this distribution you get xt, and then you compute this loss, that is so phi is encoder, right? Theta is decoder. Yeah, theta is decoder. It's the decoder network, parameters of the decoder network. So this xt is noisy image, right? Noisy image. Now I pass noisy image through the decoder theta and predict what the denoised version should be. Now this is a predicted clean image. So the objective is what? So I want to update the decoder parameters such that what it predicts is close to my real ground truth image. So that is how you train the DDPM. So what we are doing is, while training, uh, so this is how at different time steps the noisy images would look like. So you choose some random t, suppose this time step, say it is some 50, suppose t is equal to 50, and I get this noisy image. I compute xt using that equation which I had, right? So this xt, I pass it through the decoder, I get this, I put this loss, I compute the gradients, and I update the network with respect to it. So I keep sampling different time steps throughout. So t is sampled throughout uniformly between 1 to 1000, right? So it means at whatever stage I give, the network is learning to denoise the image based on the noisy image and the time step. So given that as input, it should learn to denoise it and give it, and you apply this. So this is how you train the decoder. So fine, now we learned how the decoder is trained. What about the encoder? Is there something to train there? So we use a neural network to do the decoding part. Do we need a neural network to do the encoding part, or is it not required? So there is no neural network as an encoder here, because the encoding is just that equation, right? Like this equation which we have, this thing, this itself is what we are doing. This itself describes the encoder process. So we do not really have any network because of the schedule which we are defining. We do not have any encoder network, but we need something to decode because we start from a noisy image. At the end, we need a decoder. Even in VAE, we needed encoder to learn the encoder. I mean, to understand how the latent. To learn a transform between the input images to the latent. But here, going from the input images to latent is already defined in a very clean manner. Like it's not an encoder. Like you have this sequence of Gaussian random variables by which you are encoding it. To decoder you always need, right? Because starting from noisy image, I want to come to real image space. So that is why you need a decoder in VIE, and also here also you need, just that you will do the decoding in multiple time steps. So how do we do inferencing using DDPM? We start from a noisy. So start here. Sample a noisy image. Then so you start from here and you keep going one step at a time, denoising them, following this formula. So this xt minus 1 depends on what your next latent is. This is the noisy image, like xt, and this is what the network predicts. Like you pass this through the network, you get this, right? You get this here, and z is a random variable. So you keep doing it from repeating this from the last time step 1000 to 1, and eventually you will get x0, which is a real, fake image generated. You only need a decoder here. So here what we are doing is we're predicting the denoised images, right? So there's another version of it where instead of predicting the denoised images, they predict the noise, the amount of noise we added. So when we are going in the forward pass, obviously we have added some amount of noise, right? So instead of predicting noisy images, you can predict the noise as well. So instead of all this xt blah blah blah, you will have epsilon replaced with epsilon. Okay, I don't think I have put that equation here, but anyway. Yeah, if you model the network to predict noise, so instead of the loss being over xt, it will be over this. So here epsilon naught will be the noise added, and this is the predicted noise. Epsilon naught t also would be there. And the equation also slightly changed, which will involve the predicted noise instead of x cap of. This is just algebra, there is nothing crazy about it. Rearranging the equations, I think. So to summarize what we are doing in diffusion models, it can be thought of as a Markovian hierarchical VIE. With some conditions. Obviously the latent dimension is exactly equal to the data dimension. That is, so my latents are all, it's the same size of the image, right? If my image is like 100 cross 100 latent, then every intermediate latent, so x1 to xt, all are 100 cross 100. So there is no, unlike VAE, there's no dimensionality reduction. You're completely operating in the image space. The latents are also images, right? They're just noisy images. So it is just it's an encoder and it's a decoder, but there's no dimensionality reduction. So the structure of the latent encoder at each time step is not learned. It is predefined as a linear Gaussian model, right? That equation, the form which we saw, right? So that form is the encoder. And at every time step, the Gaussian is centered around the output of the previous time step, right? So like xt is centered around what? Square root of alpha t xt minus 1. So at every time step, the mean is centered around the previous time steps. So this is the encoder form, and yeah, so the Gaussian parameters of the latent encoders, these parameters which define the Gaussian of the latent side, they are chosen such that at the final latent time step, so capital xt becomes Gaussian. So it is a variation, that's why it's called a hierarchical VIE. So although the architecture, everything remains same, there are three different equivalent objectives to learn diffusion models. One is to predict the original source image from its noisified version. That is, starting from some xt, you pass it through theta, you predict x cap t, pass the previous one. You pass xt to the encoder and you expect it to mimic what you are not generate a real image or mimic the original source. And another one where you predict the original noise, the noise added instead from its noisified version. So you take the noisy image and you predict the noise added. You predict epsilon. And there's another thing, one direction, where they call as something called score function. So you take for the decoder, you give the noisy image and you learn to predict its score. So all three are equivalent objectives and you train diffusion models with those objectives. So yeah, let me discuss some questions. So suppose I have, I'll show you these matrices. Yeah. Anyone wants to take a guess on what the question is? So where did we discuss matrices today? Transition matrices, like, yeah. Okay, you had asked a question. We discussed that latents are sampled from standard Gaussian. While x naught is scalar, how can... Oh, no. Uh, it is not scalar actually. So these are simplified examples where you are seeing everything in one dimension. But when we say they are sampled from standard Gaussian, so the latents are actually in that dimension. So it's a standard Gaussian in 100 cos 100 dimension, not a scalar. All x naught, even x naught is not scalar, right? X naught is a real image. Those trajectories all we saw is like, it's like 1D diffusion, how it would happen. But you have to think the same thing happening in much higher dimension. So yeah, they're not scalars. This discussion is for simplicity to say this. Okay. So it would be like, if it's a 100 cos 100 latent, that is 100 cos 100 dimension mein Gaussian it is. That. So transition matrices. So what are the properties of transition matrices? So DDPMs are modeled as a Markov process, right? Which follows the properties of the transition matrices follow the Markov property. And so which of these are can be transition matrices for some Markov chain? What is that defining property of a transition matrix. Row sum equal to 1. Yes. So which of these would qualify? So which of these could qualify? A and D. Right. Here this sums to 1, this sums to 1. And here what do we have? 1.5, 1.7. And here this sums to 1, this sums to 1, but the first one doesn't sum, so it's not. Here this sums to 1, 0.8, and this sums to 0.7. So this is not possible, this is not possible. Okay, so this sums to 1, is it? Yeah, this sums to 1.6. So A and D are qualified to be transition matrices. Okay, yeah, let's do one more thing. So we saw that one diagram, right, where I saw the Markov chain. So how do we visually write a Markov chain, like for easier understanding? So this is how we draw those Markov chains, right? Yeah, in this form. So now we have, so from here we can write state transition. If we are given this and we know these probabilities p11, all of this, then we can write the transition matrix. But starting from the transition matrix, we can also write this Markov diagram. So shall we try to write those diagrams for this? So if the first one, how many states are there in the first one? There are two states, right? X1 and X2. It's a 2x2 matrix, so there are two states. So this, so can a Markov, transition matrix be rectangular, or are they always square? They are square matrices, right? Where there's an n cross n matrices where n is the number of states. It defines the number of states, and row sum would be equal to 1. So here, so what does this number represent? This is 1 2, right? This is p11, this is p12. This is probability of going from state 1 to 1. So from state 1 to 1 I can't go, it says, so there is no connection between that. The probability of going from state 1 to 2 is 1. So we go this way, and this probability is 1. What about this? From state 2 to 1, the probability is 1. From state 2 to 2, it's not, right? So here, there are three states here, right? X1, X2 and X3. So I'll start from X1. So tell me the connections between X1 to other. What all does it connect, and what are the probability values? Okay, oh, this is not this, right? Okay, let's not do this. Okay, this one we can try. There are 4 states. Now this is we know that this is a Markov chain, represents a Markov chain. So can someone tell me what all does x1 connect to from this matrix? X1 connects to x1, x2, x3, x4, right? Yeah. So x1 connects to x1 means there's a self loop. It connects to x2, it connects to x3, and it connects to x4. And what are the probability values for each of them? So what is this value? x1 to x1? 0.12. And what about this? It's the second one. 0.13. And x1 to x3, this is 0.65 and this is 0.1, right? So now you know how to put the probability numbers. Now so what all does x2 connect to? X2, and it doesn't go anywhere else, right? It just has self loop. So this shows, so when moving around in this chain, if you come to x2 you can't go anywhere else. That's like an endpoint, right? Because it can't go to any other place. Or forgot the term of what this it is called. There's some definition. Anyway, okay, what all does x3 connect to? x1, x2, x3, x4, right? So x1, then we have x2, then we have 2x3, so there's a self loop, and then we have x4. Now you know how to put the numbers, right? I'll not put them. And what about x4? x4 also connects to all of them, right? So I have one that goes this way, one that goes here, one that goes here, and one self loop. Now I'll write a Markov chain and we'll write a transition probability matrix for that. So I have written some numbers. By looking at them, can you say are these correct? wrong for x1. It doesn't sum to 1. 0.2 and 0.6. I have only 2 now. I can't. Yeah. What about x2? Okay, fine. I changed for x1. Is it valid now? Is it a valid chain now? X3 has x3 has 2 connections. Okay. Yeah, I didn't notice that. Fine. Maybe I'll do it this way. Is it valid now? But do the probability sum up correctly? Sum is not 1 at x3. 0.5, 0.2. So I can make this 0.3. Okay, I fixed x3. Is it valid now? Is it a valid chain? You check 2 of them. What about x2? Anyone else? Is it a valid chain? It doesn't sum, right? At x2, what the outside going directions are? So I have 0.5 here, and there's one more self loop. 0.5 plus 0.3 is 0.8, and I have one more here. It sums to 0.9. It doesn't sum to 1, right? So it is not a valid chain. So can someone tell me how this type out this transition matrix in the chat? So this is a 3x3 matrix, right? Can someone write what this 3x3 matrix is? What should this P be? Tell me the first row. 0.6 and 0.4. Second one would be x2 going to x1 is 0.2, then 0.3, and the third one going to. And what about the third row? x3 goes to x1 with 0.3, with x2 with 0.2 probability, and it stays at its own state with probability 0.5. So this is the transition matrix for that for this Markov chain. Okay, and this question seems nice. So suppose my initial data point is x naught, which is equal to 3, and I've set the noise variance, not noise variance, the parameter alpha fixed for all time steps. Say alpha is equal to 0.6 for all time steps. Okay, then how many time steps would it take for the variance of the noisy samples to reach 0.99? So we have this equation, no? X t is equal to this conditional distribution. Square root of alpha t bar x naught plus 1 minus alpha t bar into I. Where alpha t is equal to product of 1 to t alpha I. So what do I mean by the variance of noise? So this is the noisy sample xt, and the variance of this is defined by 1 minus alpha t. So variance is defined, variance of xt is equal to 1 minus alpha t bar. Now what do I want? I want this to reach 0.99. At what time does given my alpha is equal to 0.6 for all t, at what time step will this become 0.99? Can I give you a couple of minutes? Can someone solve it? I mean, if not the number exactly, how do you approach it? Let's just put things down here, no? So alpha t bar is this. So what is alpha t bar in this case? Point 0.6 to the power t. Yeah, it is alpha to the power t. It's alpha. Yeah, as alpha is same, it becomes alpha to the power t, which is 0.6 to the power t. Now if you put it here, this variance will become 1 minus 0.6 to the power t. And what do we want this to be equal to? We want this to be equal to reach 0.999. 0.99. When would it reach 0.99? That's the question. So we want for what t this happens. So what do we have? 0.6 to the power t is equal to 1 minus 0.99 is equal to 0.01. So t is such that it satisfies this, right? Yeah, so this is how you can choose alphas like schedule. That in 1000 steps I want the variance to become 1. Means how do I choose the schedule? Yeah, there are some, I think some cosine schedule, and yeah, I don't know the details of the scheduler, but yeah. So here it is fixed alpha, but like alpha is also varied with time in some way, so that you reach it in. So yeah, until now we discussed diffusion models, right? That is, so I start from a noise vector and then I generate images. So that's like just generating random images, right? Which supposed to look like real. But practically we want to also condition this, right? Suppose I want to generate like a cartoon version of me, or like create characters of myself, change styles of something. So here I have a condition, that is I'm giving content to the model and asking it to generate based on that. Or I say I want to generate a dog, I want to generate a cat. So here I'm not starting purely from noise, right? I'm imposing the generation conditioned on something. So these are called conditional diffusion models. So conditional diffusion models, so what changes is in this diffusion process, uh, apart from what we have, the latents, we also have another condition called y. So that makes this whole process conditional. So I can you also discuss coding parts on DTPMs? Oh. Mm. Okay, wait, let me see. I didn't actually look up for any coding material for this. Anyway, so you can so when are all these conditions happen? Like text-based image generation, what we do, text-based generation, right? Like when how do you guys use GPT, Gemini, and all to generate images? You give some text and ask it to generate. So you give text, so that text is the condition, or it could be improving the quality of an image, changing characters. You give your own image and ask it to generate. You in different scenes and so on. So all these forms are actually conditions which are you giving, which forms this vector y text based generation, style, image conditioning, etc. All these are conditional diffusion models. Shall I discuss the code part next week? Like maybe in for the first 15-20 minutes, I'll discuss that code, find some simple code, and I mean I'm aware of things, but things which we use to run by benchmark and those kind of stuff. I don't as of now have a I've not found a resource like that is very simple which I can easily go over for you guys. So maybe I'll search for it and next week we can go over it. Is that okay? It would help us solve in solving the assignment. Oh, when is your deadline to solve the assignments? Tomorrow night. found something. Oh, but is this file loading for you? The GitHub thing which you shared. It shows invalid notebook to me. Okay, fine. Okay, maybe I'll just go over this one. You can see this, right? Okay, I'm literally going over this for the first time ever, so pardon me. So anyway, so in this, what do we need? We need to define a decoder, and then we need to define the forward process. The forward process is where we are adding noise. So we need a function to add noise, and then one is the decoding process, that is you pass it through a decoder network, that is typically a unit. You pass it through a unit to get the denoising image, and then we have all those that function, right, like for inferencing, where you give this input and then there's that big equation to get the denoised output, something like that. So let's just see the fundamental elements required for it, I would say. So these are all like building blocks for the network, like the build, residual, downsample, upsample. So this is all for the unit. So some things, yeah. So anyway, let's just assume, so you have a unit, whichever, that is your decoder, right? You build a decoder, so you define a class, so this is your decoder, right? A huge network, whatever you want, you build. And then, so these are the schedules. Oh yeah, these are the schedules for beta, or so beta t is basically 1 minus alpha t, right? So how you are defining, you have, say, if you define like 1000 time steps, how do you get your intermediate? So linear beta means you start, it's a it varies linearly between 0.00 whatever the two betas you define. So this is a linear beta schedule, quadratic, sigmoid, cosine schedule. So this is your noise schedule, which defines the parameters of the Gaussian random variables in your in the denoising process, right? So here they will define the number of time steps. So here they've set t as 300 and get the schedule. So they use the linear beta schedule. So what do you get? You get 300 beta values, right? Which is beta 1, beta 2, so on till beta t. And what is your alpha? Alpha is 1 minus beta t, which is the formula which we used. And the cumulative product. So why do we need this cumulative product? We did that alpha t bar, right? Alpha t bar, which is a product of all alphas until that time step. So they compute this cumulative product, that will have, so this vector will have the values alpha 1, then alpha 1, alpha 2, alpha 1, alpha 2, alpha 3, and so on. So you have, so this is basically alpha t bar. Alpha's cumulative product, previous one, so that means alpha bar t minus 1, square root of alphas. So yeah. So fine, so suppose we have this input image, what do we have to do? So okay, this first thing is find the transforming it and some pre-processing on the image. So this is the reverse transform to bring that to, like, after whatever mean variance normalization, back to PIL image, right? So yeah, so this is the forward process. Here what they've written is, so xstat is the input true image that is given, and t is the time step, which say I have, say, from 0 to 300, it could be any value, it could be some 500 or something. So you could either give a noise, or if you don't give a noise, you sample one. So basically sample that epsilon. So once you sample epsilon from square root of alpha, so this is that square root of alpha t which they compute. Square root of alpha t in yeah, from that product, and given the time step, you compute. So basically from this matrix you're fetching the teeth value, so that gives this, fetching the teeth value, yeah, and square of 1 minus alpha t. So they've literally written what we read in this. So square of 1 minus alpha t. So why do we need this for the mean component, right? That is square root of alpha t, and this is the variance component, square root of 1 minus alpha t bar. So this is the mean variance. So what is the next, like xt? Xt is square root of alpha t bar into xt, x naught plus square root of 1 minus alpha t bar into noise. So this is the noisy sample. So you given the initial sample, you gave the time step, then you got the noisy sample. So when we want to get a noisy image, you give the start image, give the time step, so it will sample from this function. It will sample from this function, and to visualize it as an image, you can turn it back to a real image, right? But that is all in normalized space. After that mean variance, denormalize it to see a real image. So this is just for visualization, but this is what you would be using Q sample in your process. This is just to visualize what it is. So here they've taken, for example, at 40th time step, how would the noisy image look like? You gave the original image and the 40th time step, and this is how the noisy image would look like. So here I think they visualize it for different time steps. So it's like 0 clean image, at 50th step 100, 150, 200. See, at 200 itself it looks like Gaussian noise to us. So even that is good enough number of time steps. But they have chosen 300 steps, right? So this is the loss function. So what do we give here? The noising model. So this will be that U-net. This is the original image, and T is the time step. So what do? First we pass the original image and the time step. Either give the noise vector, or it will anyway sample it. So anyway, you get, basically you are getting this kind of images, right? Whatever you are seeing, this noisy image. So once you have this noisy image, you pass the noisy image and time step through the denoising model. So the U-net takes only these two inputs, the noisy image and time step, and it gives out the predicted image. So you get this predicted image, and then you apply loss over that, which is like mean square error loss. Here they've defined different losses, but yeah, it's a mean square error loss. So that's how you get the loss function. So what do? We have an original data set on which we have to train a model and optimize using that loss, so that you learn that U-net. So for this they use what? They use as fashion MNIST dataset. The image size is 28, so it will be like 28 cross 28 latent dimension. So this is just image transforms, get the dataset basically, and so this is how a data loader, blah blah. So here you are defining the model and the optimizer, the model and its parameters. Now we'll see how the training loop is. So you have number of epochs, and then you iterate over that MNIST dataset. You get a batch of images. Once you get a batch of images, what do? You add time steps to it. What? Uniformly. So between the range 0 to 300, you sample those many numbers, right? 0 to time steps. Time steps is set to 300. I randomly sample one number of dimension batch size. So if I have a batch of 100, I sample 100 time steps, one for each image, and then I pass it through this function p losses, which takes in the model, your input data, and the sample time steps, and it calculates the loss. So where is that p losses function? This is the model, this batch of data, batch of time steps, you pass it through, get a batch of noisy images, pass it through the unit, get predicted noises for that whole batch, and then compute a loss, right? It'll be like 100 noisy images, 100 predicted noises, and you get the loss. So you back propagate through it and update, and basically this is how you learn the unit. So yeah, once you learn the unit, then you do what do you have to do? You would have to do the sampling, that is to generate new images. To generate new images, they have defined this function called sample, right? Where you pass the model, image size, and batch size. So image size is what 28 cross 28. Number of channels is like RGB or not. I think that's what they pass. So I want to sample 64 images. So that's what they're doing here, right? So let's look at the sampling function. So where is the yeah, here is the sampling function, and then they're calling this other function p sample loop, where you pass the model. So what is the shape? So this is what your what the noise vector shape would be. That is batch size. So they say they pass 64. So 64 images, 3 channel images of size 28 cross 28. So this would be the dimension of what our noise vector. So if you just pass this whole shape to this loop, you first sample the noise, pure noise, which is of this dimension, right? That is for 64 images, how much noise you want, you sample that. Then you do this iteration. So this is reversed from the range 0 to time steps. So it'll basically, the I will go from 300, 299, 298 and so on. Sampling group for yeah. And for each of them, that time step, I have this piece. So this is the denoising part. So that one they call this model x and t. So you compute that beta t is that there's that equation, denoising equation. From that, yeah. So basically compute your mean and mu and mean and variance using this equation, and get the denoised image, basically getting xt minus 1 from xt. uh, yeah, you can actually, I mean, carefully look at it from the paper to this. You can map it, I think, but overall that's what. So at every step I'm doing one step denoising. So here they're just appending it so that they can see the whole denoising process. Yeah. And yeah, so they're appending all of them, no? Like this one is the last image, that is the last clean image. They look at. I know I rushed through it, but yeah, that's the overall important blocks of this DDPM training and inference. Okay, then that's all I have. Thank you, everyone. We'll end the session. See you next week.